Let's dive into the magic behind one of the most common yet amazing devices in our lives, the electric motor. I mean, think about it. Motors are absolutely everywhere. The fan that's cooling your room, that electric toothbrush, your car, the list goes on and on. But have you ever really stopped to wonder how it all works? How does something you can't even see, electricity, create a force powerful enough to spin a blade or turn a wheel? Well, that's exactly what we're going to break down. So, the secret, the real key to all of this, lies in the incredible relationship between two fundamental forces of nature, electricity and magnetism. They're like two sides of the same coin, and an electric motor, well, it's the perfect example of their partnership in action. Okay, to really get how a motor works, you just need to understand two kinds of magnets. First, you've got your regular permanent magnet, like the ones on your fridge. Its magnetism is just always on. But then you have the really cool one, the electromagnet. This one is special because we can control it. We can turn its magnetism on and off, and we can even flip its north and south poles just by changing the direction of the electricity. So, what is an electromagnet really? It's all about this one core principle. When you run an electric current through a wire, that wire creates its own magnetic field. That's it. This whole idea, called electromagnetism, is the absolute foundation of every single electric motor. Put simply, electricity makes magnetism. All right, so we've got our players on the field. We have the permanent magnet, which is always on, and we have our electromagnet, which we can switch on and off with a current. Now let's see what happens when we put them together. This is where the magic really starts. This interaction is called the motor effect. When our wire with the current flowing through it, our little temporary electromagnet, is put inside the magnetic field of the permanent magnet, it actually gets a push. It feels a real physical force. And that simple push is the basic action that makes the whole thing work. Now, to really take advantage of this push, a single straight wire isn't going to do much, so we get clever and shape the wire into a rectangular loop. When we put this loop between the north and south poles of our magnets, something really cool happens. One side of the loop gets pushed up while the other side gets pushed down, and these two opposing forces, well, they create a turning motion. They make it spin. So we've got rotation. The loop is spinning, and you'd think, great, problem solved. But not so fast. We immediately run into a huge spin-killing problem. So for that first half of a turn, everything is just perfect. You've got the upward push on one side, the downward push on the other, and they're working together beautifully to get that rotation started. But watch what happens right after that first half turn. The side that was being pushed up is now over on the right, but that force is still trying to push it up. And the other side, which was being pushed down, is now on the left, but the force is still trying to push it down. So the very forces that started the spin are now fighting against it. The loop just gets stuck, wiggling back and forth, unable to complete a full circle. So what's going on here? Why does it have this, catastrophic failure? Why can't it just keep spinning all the way around? The problem is that the up force is basically stuck to one side of the wire, and the down force is stuck to the other. To keep the rotation going smoothly, right at the moment that loop flips over, we would need to magically switch the up force to a down force and the other way around. We need a way to reverse the push at the exact right moment, every single time. So how in the world do you automatically flip those forces at that perfect half-turn moment? Well, the solution is one of the most brilliant and honestly, simple little pieces of engineering you'll ever see. The hero of our story is this little device called a commutator. All it is, really, is a metal ring that's been split in half with a little gap between the two sides. And this simple split ring is the key to everything. Okay, so check out how this works. You have these stationary carbon blocks, called brushes, that feed electricity to the commutator as it spins. For the first half of the turn, the current flows in one direction, causing the spin. But then, right as the loop gets vertical and starts to get stuck, that little gap in the commutator slides past the brushes. The two halves of the ring now touch the opposite brushes. This instantly reverses the flow of electricity in the loop. And by reversing the current, we reverse the forces. The side that was being pushed up is now pushed down, and that gives it the kick it needs to keep spinning. It's a perfectly timed automatic switch. All right, now let's put all the pieces together and see how this creates the powerful, reliable motors that pretty much drive our entire modern world. So here's the whole shebang. You've got the stator, That's the stationary magnet on the outside. Then there's the rotor, or armature. That's our spinning electromagnet in the middle. Attached to the rotor is the commutator, that clever split ring. And finally, the brushes, which are the stationary contacts feeding power to the whole spinning assembly. These four parts work together in perfect harmony, turning electricity into motion. So, what if you want to make the motor more powerful? Well, it's pretty simple, actually. You can pump in more electricity, or you can use stronger magnets for the stator. Or, and this is what you see in most real motors, you just add way more loops of wire to the armature. The more wire you have, the stronger your electromagnet becomes, and that means you get a much more powerful spin, or what engineers call torque. And this elegant solution, just using a split ring to constantly flip the poles of an electromagnet so it's always being pushed around by a permanent magnet, it's the driving force behind almost countless devices we use every single day, from the smallest toy to the most powerful electric cars. What this really shows us is that a lot of times a really complex and powerful device is built on a simple, brilliant idea. Once you understand that little dance between the commutator and the electromagnet, you start to see all this hidden ingenuity around you. And that kind of leaves you with a fascinating question, right? What other simple, ingenious inventions are hiding in plain sight, quietly powering our world?